haven't met me yet, my name is Haley. I am an officer in Appin Club. I'm currently a junior in New York City, being in the Chapin School. And if you're new here, welcome. And if you're back for week 2, welcome back. I'm really happy to see you guys. All right, so let's start. Just as a heads up, this week's lecture is going to be really packed. Get ready, I believe in you. What is computer vision? Computer vision is basically a field of computer science focusing on analyzing and processing images or videos like how humans would. By using logic and image processes like humans, this enables machines to learn and understand things in front of them using a camera and even visualize and react to surroundings that they're in. They do that by examining the relationships of different pixels of an image they're told to process, and they can identify meanings through training and validation. The trained machines are called the algorithm. By the way, the algorithm may sound like a really fancy term, but it basically just means a machine that can identify a pattern because they're trained on it. Okay, how does it work? I've touched on it a bit, but with more details. Computer vision technology tends to mimic the way the human brains work. But how does our brain even recognize images? We usually just take it for granted. Well, first of all, we really are not sure ourselves. One of the popular hypotheses in neuroscience said that our brain relies on patterns to decode individual objects. And that is exactly how computer vision works too. We train computers in a massive amount of visual data. Computers process images, label objects on them, and find patterns in those objects. For example, if we send 1,000,000 images of flowers, the computers will analyze them, identify patterns that are similar to all flowers. For example, they see that all flowers have petals, let's say, and they have beautiful patterns, and all of them have green leaves near them. And at the end of the process, it will create a model called flower. As a result, the computer will be able to accurately detect whether a particular image is a flower every time we send them pictures. And of course, the accuracy increases the more data that we send them. Here are some subdomains of computer vision processes. We're going to go over most of them today, so this is just an overview. Image pre-processing deals with the low-level features of images. It is basically making an image easier to understand for computers before even processing it. That is why it's called pre-processing. Anyways, the feature detection provides a refined representation of images. Segmentation detects the parts of images. 3D reconstruction, we're not going to go into that in depth today, but creates a 3D model of objects from 2D images, which is really cool. The object recognition labels what appears in the image. And lastly, motion analysis deals with moving objects in videos. Image pre-processing. As I said before, it makes an image easier to understand for computers. There are a lot of ways that you can do that. Imagine like you're putting on different glasses to look at the world. Some examples are brightness, contrast, color normalization, and filtering. Well, before that, let's start with pixels. So, for computers, all images are just codes with pixels, like the speech bubble, for example. This bubble, from background color, its filling color to its outline, are all pixels to a computer. So this speech bubble, for example, from its background color, its filling colors to its outline, are all pixels to a computer. And every color of its pixel have a name. For example, excuse me. 0 means black and 255 means white. Well, of course, this is how a computer sees it, because it can't comprehend color how we see it. Now, knowing that, we can go on to see how computers can manipulate images. Brightness. As I touched on a little last class, computers will see color in codes. and they have the ability to make the pictures brighter or darker by adding value to the code. They can also multiply something to the code to create a larger contrast, as you can see here. The background of the penguin, let's say, is clearly lighter than before, and the color of the penguin is darker in contrast. And there are things. Color normalization sees how much red, green, and blue are in an image compared to the other colors. It enhances specific color features or remove irrelevant color information for better analysis. And by doing that, it improves the consistency of the original image. Filtering combines each pixel with its neighbors, and by doing that, changes the image in terms of its clarity and its position. You can, let's say, move the image to the left, right, up, or down, or you can make the image more blurry. Okay, now let's watch a video about how exactly computer vision can work.
Hi, my name is Alejandro Carrillo, and I'm a robotics engineer at an agricultural company. Specifically, my team uses machine learning and robotics and computer vision to identify the difference between the crops that we eat and weeds that take nutrients away. And we're able to remove those weeds without any chemicals.
My name is Kate Park, and I work at Tesla Autopilot. I build self-driving cars. Any place where there can be resources used more efficiently, I think is a place where technology can play a role. But of course, one of the best impactful ways of AI, I hope, is through self-driving cars. Have you ever wondered how a computer can recognize a face or drive a car? Or maybe you've wondered why it's so hard for a computer to tell the difference between a dog and a bagel? Well, it all has to do with something called computer vision, the way machines interpret images. Let's take a look at a simple example of how computers learn to see.
Here are two shapes, an X and an M. At some point, you've learned the names for these shapes, but a computer looking at these images for the first time just sees a bunch of little squares called pixels. Each pixel has a numerical value. For a computer to see, it needs to make sense of these numbers to figure out what is in the picture. In traditional programming, you could tell the computer to check which pixels are filled to decide what shape it sees. If the center and corner pixels are full, then it's an X. If the center and corner pixels are empty, then it's an O. Traditional programming works great for this kind of thing. But what about asking the computer to recognize these images? What might the computer think these are? We gave the computer a strict definition of what an X looks like. But these images don't fill all the necessary pixels to fit the definition. So if the computer doesn't think these are X's at all. In fact, the computer thinks these are O's because the corners and center pixels are blank. And that fits the definition of an O that we gave it.
In this example, traditional programming only works some of the time. But with machine learning, we can teach the computer how to recognize shapes no matter their size, symmetry, or rotation. Teaching a computer requires thousands or even millions of examples of training data and a whole lot of trial and error. So let's start training. Here are some simple shapes we can use to train the computer to see. At first, the computer is completely clueless and makes a totally random guess from a preset group of options. And it guesses wrong. But that's okay, because this is where the computer learns. After it makes a guess, the computer is shown the correct answer. It's like learning with flashcards. Sometimes you have to get it wrong before you get it right.
With every guess, the computer looks at each pixel and the surrounding pixels. It tries to recognize patterns and make rules to help it guess. Like if it sees a row of orange pixels next to a row of white pixels, there's an edge. If the computer sees two edges oriented a certain way, say at a 90-degree angle, then it's likely to guess that it's looking at a square. It won't get it right every time, but with more trial and error, it will slowly build a more confident guessing algorithm.
Whether it's trying to guess shapes, animals, or any other category, machine learning finds patterns by learning from its mistakes. The training data is used to make a statistical model, which is just a fancy way of saying a guessing machine. When we give it training data, the guessing machine is tuned and optimized to recognize the pictures we gave it, with the hope that it will then be able to recognize new pictures with the same accuracy.
It may seem easy to tell the difference between an X and an O, or to even categorize basic shapes, but most images aren't that simple. Let's take a look at how computer vision can learn to recognize complex images, or scenes like ones in the real world. Most complex images can be broken down into small, simple patterns. For example, an eye is made up of two arcs and some circles inside. A wheel is made up of concentric circles and some radial lines. The way a computer recognizes the patterns in all these pixels by using a neural network made of many layers. The first layer of neurons takes pixel values as numerical inputs to identify edges. The next few layers of neurons take those edges and try to detect simple shapes, until finally the computer puts it all together to understand.
It can take hundreds of thousands or even millions of labeled images to train a computer vision system. But sometimes even that's not enough. Some face recognition systems have trouble even seeing people of color because the system was primarily trained with photos of white people. Sometimes problems in computer vision are silly, like when a computer gets confused trying to tell the difference between these dogs. Oh wait, that's not a dog. But it does kind of look like a dog. At least this dog.
But as society relies on computer vision for real problems, like detecting diseases in medical imagery or helping a self-driving car identify pedestrians, it becomes increasingly important that we all understand how these systems work and what types of problems they're appropriate for.
Computer vision can open up a miraculous world of possibilities, but a machine is ultimately only as good as the data used to train it.
Mm. Okay. So now we're just going to be going deeper than this into more of the algorithm side and more mathy side, just as a warning. So, segmentation. Segmentation is to find consistent regions in an image, and it'll give an outline to objects that computers can differentiate from them. By doing that, computers can identify targeted objects from either the background, like here, the human from the background of city, probably, or a squirrel from a field of grass. Or from another object, like here you can see a human being identified, then another probably human behind him, or here a hand from a ring-like structure. Many techniques are based on comparing adjacent regions. These are without classification or unsupervised learning, machine learning. Flashback to last week. Clustering and neural networks can be used to group some similar patches. For example, self-organizing maps or constraints satisfaction neural networks. So self-organizing maps, or SOM, organizes data into clusters. Similar colors will be grouped into the same group, taking in each pixel and map them to a grid of neurons. The word neurons are used here so it feels more like a human brain. Nearby neurons in the grid represent similar features, forming clusters. Imagine SOM as a painter grouping similar shades close together. Constraint satisfaction neural networks, on the other hand, are used when you want to group patches while respecting some rules and restraints. For example, it might enforce that two neighboring pixels are more likely to belong to the same cluster unless they have a very different colors. Supervised classification flashback to last week, is an upgrade. We will give them the rules that we want them to follow. For example, we want to teach them to identify a human, and even when the human is wearing, let's say, different colored shirts and pants, so that they won't be classified as one group in unsupervised learning. The goal of it is, once again, teach the computers to learn like us and to see like us, and therefore react like how we would. And as a review, unsupervised classification or unsupervised learning does not have labels, and the computers finds patterns on its own. Compared to that is supervised learning, and you can provide pre-identified labels for training. And the goals of unsupervised classification is to group similar pixels or regions into clusters without knowing the labels, and supervised learning teach the model to assign known categories to each pixel or region. And for training data, unsupervised classification uses only the input images and no labels, while supervised classification requires labeled images. Computer vision is one of the areas in machine learning where core concepts are already being integrated into major products that we use every day, like self-driving flight. Like what comes to mind when you think of how machines see? Just let me throw that question out to the audience. If you have any idea or any guesses of whether or not it should be counted as computer vision, you can put it in the chat. Yes, so yeah, the videos did mention medical purposes as well. Yes, well, you guys are basically on points. So there are a lot of examples like self-driving cars, facial recognition, augmented reality, and healthcare. And oh yes, healthcare. Computer vision, when trained well, can be basically a set of eyes of a well-trained doctor. Computers can diagnose diseases like cancer through recognizing patterns in MRI, CT scans, and X-rays. It could also assist in surgeries, where guiding robotic surgeries with precise visuals, and monitoring patients as well, tracking patient vitals through video analysis, let's say, as well as transportation. Not only automatic drivings are using it for objects like walking human detection, lane detection, and traffic signs recognition, but also a more macro level, like computer vision can manage traffic. It can monitor congestion and optimize signal timing. And last example, but certainly not the last of the possibilities, it can help the police when fighting crimes through facial recognition, sounding alarms when detecting an intrusion, and analyze CCTV footage to predict potential crimes. Of course, with revolution, technologies do come a chance in the world as we knew it, and rising ethics problems. But before that, what are some applications of computer vision that excites you the most? Oh, so it's not included in this slideshow, but the video did mention that it could help in agriculture as well. It's cute. Face ID in Apple, yes. Well, all of those fields are going to be really helpful in their lives, and all of them are really interesting as well, which is cute. All right, and let's go on to ethics problems. So the maturing of facial recognition in computers means something that, well, has never been seen before. Like using surveillance cameras and social media posts wherever you are, and you will be recognized and your locations will always be known. There may no longer be a sense of privacy that we knew today. Like the company Clearview AI in 2020 had already dropped the product known to use surveillance cameras to use computer vision to locate targeted people. A BuzzFeed review of Clearview's leaked client list reveals that as many as 2,000 228 law enforcement agencies, companies, and institutions had collectively performed nearly 500,000 searches using the app. Additionally, using facial recognition algorithms, the law enforcement may wrongly accuse someone of a crime. The algorithms have a low fault tolerance. That actually already happened. It is also in 2020 that Robert Williams was arrested for allegedly stealing thousands of dollars of watches. Detroit police had matched the surveillance footage of the crime to Williams' driver's license photo using a facial recognition service. But Williams wasn't the robber. At the time of the robbery, he was driving home from work. As already mentioned in the video, most facial recognition models are trained with white people's facial structures, and the accuracy of other races are still low. And this will definitely worsen racism in law enforcement. Yeah, and I believe that's the end of the lecture. So this is part 1, and after this, we're going to be using PoseNet and creating our own app of our own using computer vision. First of all, just as a really simple intro to PoseNet, which is the extension that we're going to be using in MIT App Inventor, it is basically a tool, which is a pre-built algorithm that is already trained to recognize key points of a body, and those are key points of the face. And we can use that to define particular postures of people. And yeah, so I am going to send you guys. I did. This is a .aia of MIT App Inventor, and then it basically have the extension that we're going to use. After you download that extension, you would go to MIT App Inventor, which hopefully you guys already created an account for. If you haven't, you can go into our Discord server and there will be people who will help you get an account, etc. So you will come to the MIT App Inventor, and then after you downloaded your thing, you should go to projects, and then there is import project from my computer, and then you would click that. So it's project, import the project from my computer. And after you click it, you will just drag or choose the file, format, etc., etc. Yeah. If you're and after you did that, it would take some while to load, but you'll get this thing. Or it has this and this thing. If you're at this point, click 1 in the chat. You won't need to open it. It will just be after you download it, you will just go into MIT App Inventor, and then they will have an import button over here in projects. So you won't need to download anything. It will just be MIT App Inventor. Again, and if you have any questions, you can always ask in chat or you can ask in the Discord. There will be people who will help you there. Again, I dropped the extension in our Zoom group chat, and just click and download it, and then you can import this extension by clicking on projects, which is on the left up corner, and there's an import project from my computer, and then you can go from there. I will send the thing again, just to make sure that everyone has it. For time purposes, I'll just start now. If you feel like I'm going too fast, please tell me, or the recording is always going to be posted on App in Club YouTube channel, and you can follow through over there as well. So, first of all, there are a lot of things for us to define. So we should know what we are working with. This is what the thing is going to be, where there's going to be a lot of lines that is going to identify your hand, your elbow, ankle, and then your face, etc. And basically, you should define those points so then when you want to use it or extract it for our purposes, you can do that. And if you don't know yet, we are going to be doing an app where when you're doing jumping jacks, the computer is going to recognize that and to count how many jumping jacks that you've done. Okay, so first of all, you're going to go to procedures, and then you're going to drag out the procedures. And then we're going to name this X. Basically, what I want this to do is that whenever we want a point, let's say I want to see what points of my right eye is in the grid that the computer is going to be understanding where my body is or where my posture is, they would only look at where what X value of that right eye is. So then it will be easier for it to process, and it will be easier for us to command in the future. And then we would make a list. Not this one, sorry. These two things are easy to get mixed up. But sometimes we're going to be using this one and sometimes we're going to be using this one. And you can see that this time the puzzle piece wouldn't match up, so we need to use this. And going back to our list, we're going to be using select list item list, which is, you might need to scroll a bit, it's over here. And then you're going to click on input X over here. And then this thing is going to be called point. This is just a local value. You can call it technically anything you want. And then the list is going to be get point, which basically, this is just a procedure that we will teach the computer to do. And whenever you call this procedure, it is going to extract the value that you want it to be. And then the point can be anything that we want, that we are going to give it in the future. And then for index, we just put 1. 1 means that it is going to be in the x coordinate, and 2 it means that it's going to be in the y coordinates. All right, if you're following, press 1. So for a point thing, you will just click the setting-ish thing, and then you have inputs, and then you will just drag the input over here, and then it is going to add a new variable to the procedure. Okay, so I'll continue. The next step is pretty easy. So this is for the x coordinates, and then we just copy and paste it and make it the y coordinate. And then because of that, the index is going to be 2. Because what I'm doing here is essentially I am only telling the computer to give me the location data that I want. So then, let's say for jumping jacks, right? I want to see if the two hands are close enough together in the x coordinate, and therefore I won't need the y data, and that's why that I would separate them, because sometimes I won't need one or I won't need the other one. Okay. Okay, for time purposes, I'm gonna speed up a bit because this one is pretty long. Okay, so after this, we are going to need another procedure. Still this one with the puzzle piece thingy. And then we are going to make an equal definition. And then we're going to go to list again. Gonna click length of the list. Oh, and also for here, we're going to need another input, and the input's name is still going to be point, because we're gonna be we are talking about points right now, where we're going to be using the data of the algorithm that PoseNet is going to give us, and then we are trying to manipulate it to the way that we want it to be. And the length of the list of the points should be 2. Like this. If you have any questions, if you're up to this point, press 1 in the chat.
Hello, Haley.
Yes.
Hi, sorry. I just on the main website. How do you get to where you are right now on the screen?
Oh, you mean so you just click blocks over here.
Blocks? Like where's that at?
It is going to be on the right hand up corner. Like you are here, right? And then you will click blocks.
No, I mean the main website. I just cut in. I started late. Sorry. On
Oh,
the
I see.
MIT App Inventor. Like how do I get to where you are?
Right. So, first of all, you will need to download the extension, which I posted in the chat. I'll post it again. It's this one. And then afterwards, you are going to click, after you download this, you won't need to open it. But after you download it, you will click projects and then import project from my computer. And then you will just drag the downloaded file over here, and then you will get this thing.
Okay. But when I sign in the MIT App Inventor website, is that do I press get started first or which part?
Oh, so for that, because that we did go over it last week, you can go to our Discord and get started from there. But first of all, you will need to let me go to the MIT app. You're in the main website, right?
Yeah, the main website.
I will get automatically logged in. But there is going to be a button over here that says create an app or something like that. And then you can click that.
So the main website, go to the create apps, right? .com. I mean
Yeah.
see, main website.
It's going to be somewhere in the top left corner. But if you have more questions, do you have our App and Club Discord?
No, what's the Discord again?
Can someone in the officer send the link of that Discord, please? Perfect. So over there you can join and
Okay, so from Discord I can join the project then?
yeah.
Okay. All right, so I'm on Discord right now. So where do I go to, Haley?
Oh, there will be people who will guide you individually when you ask questions.
Okay. See. Hmm.
Again, and I also didn't um thank you, Yumeng. For this procedure you can just call it defined because this thing we are just defining the points. Okay. And you get the points from wait. Okay, that's weird. I'll make this the current section. For points, again, you will click this, and then there will be input, and then you just drag the input over here, and then it will make a variable for the procedures. Okay, so I'll continue. Yeah, of course. And then you will need another procedure. There are a lot of procedures because then, instead of like because we will be needing these steps a lot of times, and then if we don't define them beforehand, we're just going to reteach the computers over and over again every time we need to make these procedures. So it will be easier if we just define them now. This is defined. Oops. Okay, so this one is going to be pretty complicated. So let's call this all defined. And then put an input over here of okay. So what we do now is that we click into variables and then we have initialize local name to, and we name it and then we go to logic. And then we'll go to control and then we scroll down to this one. It's called do, and then there's a result there. It's like basically at the end. Drag it down here. And then you go up. Click this. Okay, I'll do this. And then you get the list of points like this because this is the list that you want. And you drag an if statement. So if the all defined Yeah. So if you get up to this point, press 1 in the chat and then we can wait. This block is pretty complicated as well, so don't worry if you're like not as experienced as navigating MIT App Inventor. Oh, I know. So if you haven't noticed yet, you probably have, but like each of the color of the blocks uh resonates with the color over here. So like if you see that this is orange, and it's definitely, unless it's going to be in the components block, because then that will be different. But for now, the orange block is going to be in the variables. Okay. I'll wait for like maybe a few minutes right now. And also, again, I've said it before, but like, if you want, let's say, a environment where you can pause me and do the app on your own, you can always go to YouTube. This session is going to be posted there in a few days, hopefully, and then you can get more self-paced as well. Okay, I'll continue. So you go to procedures, and you have call all defined list of points, and then oh wait, actually no. You call defined, which you are referring back to here, and then the points is just going to be get point. Then you would set the all defined to false. What this thing do is basically if this thing didn't work, right? If this thing did not work, then the all defined is going to be false. And then basically it means that the extension for some reason stopped working. Like maybe a human is just not in the camera and then they cannot like find the human. Then it will like it will pause its algorithm so then like it won't crash. And yeah. And then therefore the result is just going to be get. All right, if you're at this point, press 1 in the chat. Okay, so I'll continue. So after this, you'll define other things. Like as I said before, I'm going to look at the difference between the x coordinates of two different points. So let's say it is my right hand and my left hand. So I'm going to have a procedure where it's going to calculate the distance between them. And we can do that by getting another procedure. And then we can call this distance x. So in order to make it so then it's less complicated, I'll just add the absolute value here, which means that if I wanted to say if this thing are close enough together, making it like 10 values apart from each other, then something would happen. And what if that, like, for some reason, this thing became -10? Then that is going to And then if it is apart, then it's going to be negative 300. And that would still be less than 10, but we don't want that because it is really far together. So therefore we need to add absolute over here. And then after we added absolute, we're going to use the minus sign, which means that we want to minus one x value coordinate to the other. And then we're going to call x to the point. And the point is going to be there. This is an input that we're going to make. So there's going to be a lot of inputs, x and y. And this is going to be get x. And then, oh, let's make this 0.1 and 0.2. Because if we say y, then maybe it is going to be confused by the y coordinate. So this is distance x. And then the same logic, this is going to be distance y. And then because of that we should call y like this. And then, oh, the points are weird. Oh, we just have to, okay. Like this. Okay, if you're at this point, press 1 in the chat. Okay, I'll continue. So now, I think this is going to be the last one. One last of the procedures. This time, instead of the results, you do. And this is where we are going to identify if you're doing a jumping jack or not. And it's going to be called jumping jack. Yes. Okay. So what you do is you go to control, and then you pull out an if-then statement. Then you're going to call a variable. And basically what this do is, oh yeah, actually I'll explain that afterwards. And then you have a list profile. Make a list. And then now you can use your PoseNet extensions. So you're going to left. One of the list is going to be left wrist. And then the other is going to be your right wrist. And it's basically telling the computer that you're going to be focusing on these two components. For this thing, to make it easier, I'm only going to be looking at your upper body of the jumping jack, because first of all, my room, it wasn't big enough for me to test out the leg component as well. So I cut it. And also, we do have a time restraint. We have 20 minutes left. And if you want to make it for the lower body, it is going to be using a similar logic, and it's possible. So I really encourage you to try that out. Okay, if you're on this point, press 1 in the chat. All right, perfect. Then After you do all of this, you have another if then you have an if then else statement. And then you will use logic. There's this one that says and over here. And basically we need to, this thing is going to be, this is going to look a little bit messy, but bear with me, okay? So I want to measure two things. The first thing is that when you're doing the jumping jack, your two hands is going to be really close together. So I want to look at the x coordinates of my right hand and my left hand, like this. Okay. And then the second thing is that I want to look at the y coordinates, that I want my hands to be really up like this, because if it's like this and it's not like a jumping jack, and you shouldn't be counted as a jumping jack. So there are two things. Therefore, there are the thing and the and. So we can start with the distance x. And then you call off distance x. But the thing is, we need to see how much this distance x is. So you go to math, and you come over here to look at the relationships, basically. Call this as x. And then this is going to be smaller or equal to something else. So over here, that we should make a variable of what that said something else is. It is initialize global name, and then I just call it change of x. Change of x. Okay. Two, this number, you should, it would vary, and I would just say that it's 100 because this is what I tested. And then using that, you have get this thing and say that this is basically saying that if the distance between your two hands is smaller or equal to the change of x that we have, which is 100, then, and if something else happens, then it would be counted as a jumping jack. This is just going to be put over here. Okay. And what is 0.1 and what is 0.2? So what I need is the right and the left hand, right? So whatever here is the left wrist and the right wrist. It's like this. Okay, so this is delta x. If you're with me, press 1 in the chat. Okay, perfect. So now we're going to do the same thing for delta y. Okay, so it's still going to be a similar logic. You drag this thing over here. However, this is going to be distance y. Then instead of right wrist and left wrist, you're going to do your thinking. So like I'm trying to get the distance between this place and some place that's not in my arm, right? So then you can see that it is really high up over there. So I just did my right eye. And then because you want it to be as high as possible, I just it should be larger or equal to. And then now we need another global variable. So this is going to be change of y, and I just made a 40. If you're with me, press 1 in the chat. Oh, and also this should be global change of y. Distance x and distance y are procedures that I made myself, which is basically the difference between the x coordinates of points to the distance or the distance between the y coordinate of points. I'll put myself over here as well. Uh, hmm. Okay. Who needs more time? Let's see. If you need more time, press 0 in the chat. I'll continue. Okay, so now you have all of this, right? And then there is a then else thing. So the then here is just going to be telling your people, the user, that you are doing the jumping jack. So now you're gonna go to your output over here. So I'm just gonna use a label, text for label 1. So anyone can use that. So then over here, if this thing, which means that they detected that you've done a jumping jack, you can go to label 1 and you can set the label 1's text to text jumping jack. Okay. And then if you wanted to make it more obvious that like that there's a jumping jack, you can change your background color, and there's a color section to red because you can. Anyways. And then if this thing over here detected that you're not doing the jumping jack, you could say no jumping jack. And then you should set your background color to white. You can do whatever you want with the background color. All right, if you're with me, press 1 in the chat. I'll continue. So after you have all of these, okay, which is a lot, I'm proud of you guys. So now this is just all of the materials that you needed, and now all you need to do is to make them into one. So you go to PoseNet extension, and you have when PoseNet post updated. And then you can call jumping jack. And this is actually all you need. But the thing is, usually it wouldn't work. So you have to monitor step by step on what happens or like what could go wrong. Or if you just wanted to tweak your change of x and change of y, you might want to have more labels over here. So oh, and also if you want to view your webcam, you will need a web viewer. So just drag it over here quickly. And then the height and width can be a little quick. And now you can look at what you're doing. But if you want to look at things, you just drag more labels in, and then you go to over here. And then you could look at maybe set your text to list like this. So then you can look at wherever your right wrist is, or you can even look at what your distance x is, like this, like that. Yeah, you don't need to follow this. This is just this is just basically showing you a way to troubleshoot if like your coding ended up not working for one reason or another. There are a lot of factors that might lead to it not working. Like this initialized, maybe this 100 and this 40 doesn't work for like your surroundings. Maybe PoseNet itself isn't just as sensitive as we want it to be. Maybe like they can't find your arm. Oh, and also when you're testing it, I recommend like you pulling your wrist up because it would be harder for them to see what's jacket. And little things like that. So this is just a way for you to troubleshoot if like it's not working, and it can it makes the coding process more transparent and you can see how computers think. And yeah. So this is basically the end of our lectures. Thank you so much for joining me. And if you have any questions, feel free to stay behind and I will answer them. And all right. Thank you so much for joining again.